Okay. I will just talk about the legal slide once more in the meantime. Okay, just this now will extend the compiler or composer module to show you how you can use the Intel Composer to get to better vectorization. So we will start with a yet again introduction to SIMD vectorization, just a very quick one. Then again turn to reporting features. You know, I'm iterating on that because it's an important thing. Then I will tell you how to get actually vectorized code, and then how you can improve vectorization capabilities. Okay, SIMD vectorization. So the basic idea, and Chris already explained that shortly, is to have a single operation acting on multiple data elements at the same time, producing multiple data elements at the same time, right? And so depending on what is the bit size of the vector register, like SSE, it's 128-bit. Different data types, so two doubles, 4 floats, 16 times a byte operation or something. Then with AVX, we got the same, but double the width. With C on 5 SIMD instructions, we again doubled the width. So we can, for example, compute 8 double precision elements or 16 single precision elements in one single instruction and deliver that every clock cycle, basically, at least running at peak. Okay, the other thing is vectorization, as you might see here, assumes that the operation is acting on all the elements at the same time. And what happens if you got an if statement in there? Right, so typical HPC optimization rule of thumb, avoid an if statement in the innermost loop, right? That's, you know, rule 47 or something. This doesn't hold anymore, at least not in this particular case. At least C on 5, for example, and probably also other upcoming Intel platforms will have conditional vector operations. Okay, and this is basically a vector compare producing a so-called mask register. And with that mask registers, you can control where an operation, a vector operation is acting, on which data elements it is acting on. So for example, if the mask register K7 indicates a true value for that particular vector element, the arithmetic unit in the core would execute the operation on that particular vector element and would only use or update the target vector wherever the mask specifies that an update should occur, right? So now you can at least have simple if statements in the innermost loop. So rule 47 no longer holds true. Okay, and regarding the evolution of vector instructions, so with Nehalem, we basically, and this, you know, SSE 4.2 didn't bring anything for HPC people, right? So this added, you know, string capabilities and that kind of stuff. But what we got is support for fast analyte loads and stores for vectors, which was not possible in former times. With Westmere, we had new instructions like AES, also non-HPC. Sandy Bridge now is the first new processor that actually has a true HPC benefit by doubling the floating point throughput through AVX. And in future, we are thinking about, and this is no secret anymore, I can tell you that publicly, we will introduce a fused multiply add instruction. Right, so that will again double the peak performance and would do a floating point multiply and addition at the same time. And this is where Chris in his module said the floating point multiplier port and the floating point addition port will become symmetric again because both will do fused multiply add. And of course you can do a fused multiply add without addition. And you can do a fused multiply add without multiplication. Right, and then both ports can execute basically adds or mults or FNAs at the same time. That's the idea.
Multiplication or summation?
I'm sorry?
What is it used?
Well, if you got something like A times B plus C in your code, right? This is right now 2 instructions, a multiplication and addition. And with FNA, this is a single vector instruction on the machine, right? And to simulate an addition with an FMA, you just have A times 1 plus B. And if you want to simulate the multiplication part of it, you would have A times B plus 0. Right? And then you can, implement vice versa, and you get a symmetric execution part. Okay, so I'm sorry, this is yet another marketing type of slide. Red is bad, green is good. Okay, marketing. So on our machine today, if you get sequential code, no vectorization, you lose almost all the benefits of the machine. Right? You get a single core with scalar instructions. If you add sequential code, but it's fully vectorized, you gain, at least theoretically, a factor of 2, 4, or 8, depending on the data type that you're computing. Same for multi-threading. So best use of the machine you can make when you have multi-threaded vectorized code. Okay? And this is true for all upcoming Intel platforms, or all upcoming computing platforms. Right? It's not only restricted to Intel. I'm sorry? Well, multi-threading also may mean multi-processing in terms of MPI. Okay, but generally, multiple instruction stream on the same CPU. Okay, reporting features. I deferred that slide from the earlier presentation before the coffee break. So basically, if you turn on vectorization either through O3 or -vec, you can tell the compiler to let you know about what it actually was able to vectorize and what not. There are different reporting levels, and usually the ones that you actually need are depicted in blue. So the first one is, and this is the default, tell me what loops the compiler was actually able to vectorize successfully. Okay? That's kind of the green spot. But the most interesting part is level 5, where the compiler reports what it was not able to vectorize, because that are the problematic areas in the code. Right? This is just, to go home and feel good, and this is to start working on the next day. Okay, what you get out of this, and this is Fortran. Who have used a Fortran programmer? C? Perl? Okay. So the Fortran, well, it's kind of 50-50. So this is Fortran, obviously, and now the compiler tells you that the loop in line 38, column 3, was not vectorized because the compiler thinks that there is a vector dependence. What that means comes in a second. And it says that it was able to prove that there is a flow dependence between line 39 and line 39. And if you look closer to the code, you will see that we need to compute the right-hand side first before we can store it in the left-hand side. And so we may not execute this loop, concurrently on a vector instruction. Right? Okay. Guided autoparallelism, I already told you that. That's kind of the idea, to make the compilation process more interactive, to improve the reporting capabilities, and not only report the problem, but also report potential solutions to the problem. Right? That's the key idea behind that. It is still not an automatic parallelisor or vectorizer. You still need to do it yourself, or it doesn't extend the capabilities that we have in the compiler. It does not ask you anything about changing the algorithms. Right? It will not report. You will get better result if you change your merge sort with a parallel quicksort or anything like that. Right? It will just tell you what is the current problem with your current version of the source code, and how you can easily fix that through compiler options, through very basic code modifications, or pragmas or whatever. Right? It's not suggesting a new software design or anything. Okay, and it's also restricted to what the compiler sees, and this is typically source code. Right? So no runtime profiles, no runtime input data, or anything like that. It's completely static. Okay, this is how it goes. So you start by identifying hotspots. You already know how to do that by using the profiling feature. Or we will show it to you tomorrow how you can do it in VTune. So you restrict yourselves to the hotspot because these are the low-hanging fruits. You turn on the gap feature for this particular source file, module, whatever, runtime, Fortran routine, whatever. You get the advice messages. You implement them. Hopefully they are correct. So this is your part of the story to tell the compiler or make an assessment if the code modification is actually possible or not. You get a modified source code. You feed that into the compiler, and hopefully you get an improved binary. That's the idea behind that. You know, it's kind of interactive. It's not mouse click type of interaction, but at least the compiler gives you some more feedback, and you can more or less interact with the compiler and implement source code changes. I showed that already. So in this case, the compiler thought that there's aliasing, and it tells you that f argument no alias would be a potential solution to fix this problem. Or if you do C99, you can also use the restrict keyword to mark the pointers as restricted, non-overlapping pointers. Okay? And tell the compiler, you know, you are now safe to optimize. Okay? And whether or not those pointers are overlapping, you know, that's your call. Okay. Basically, if you feed that, for example, into the compiler, it will tell you that it thinks that ne arrow len here is not constant for the loop execution. It's not an invariant because, you know, there are a couple of pointers and that kind of stuff. So there might be some way to change the storage location where the ne len is located through some pointer. And so the compiler would advise you to either create a temporary variable for that, or to use something like pragma ivdep to tell the compiler that the loop iterations are independent from a vectorization standpoint. Okay? Or what it also tells you, for example, if you get a structure in C or even in Fortran that has some useless data in there, the gap report can also tell you, hey, there's some useless data. If you remove it, then I can vectorize it, right? Because there's a hole between A and B. And if you remove useless, you get stride 1 access on the structure, and then the compiler can start vectorizing it. That kind of stuff. Okay? And these are typical problems where the programmer doesn't know or doesn't pay close attention to what the compiler needs to do with the code, and this is where this feature becomes useful.
Problem with the size of the variables, so it's not enough space to vectorize.
Now, if you got 2 integers with a hole in there, like int useless, it's no longer stride 1, and the compiler cannot vectorize. Because vectorization means that you have consecutive elements in the memory that you load into a vector register, process them, and store them back consecutively. It's the same problem with those sparse algorithms that have been discussed earlier today. So whenever there are holes in the memory access, like the useless, or jumps through a pointer array, the compiler cannot vectorize anymore. Because it's not a contiguous block of memory to load into a vector register and write back.
So if I define variable b directly after a, then it works? Or
That would work, yeah. So if you change around useless and a, it would probably work again, but now the compiler might report that a and b are no longer aligned properly. We will come to that. So there, you know, if you got useless data in there, get rid of it. That's the deal about it. Okay. Now, how to get vectorized code? There are so many pitfalls where vectorization can fail. So the most frequent one, obviously, is that we don't have independent loop iterations, like we had in this Fortran example where we had this proven flow dependence. But there are other potential reasons, like alignment, right? So whenever alignment is wrong, the compiler can still vectorize, but it might not be beneficial from a performance standpoint anymore. If there are function calls in the loop body, and there's no vectorized version of the function. This might fail. If the control flow is too complex, like if statements, if then else, try catch, whatever you might think of. Loop not countable, that's also a good one. I already showed an example with the NE arrow length. Non-unit stripe elements, mixed data types, so it's always a pain for the compiler to have double precision and single precision computation in the same loop. Sometimes the compiler is smart to figure out that it needs 2 vector registers to cope with one single precision vector register, that kind of stuff. Or simply the compiler thinks that the loop doesn't run long enough so that vectorization doesn't pay off. And there are so many more, but they are rather esoteric. So this is kind of, I would say, in decreasing probability. Okay, how can you tell the compiler more about it? Or how can you vectorize your code? Obviously, fully automatic vectorization is the way to go. That's the kind of the lazy approach. Change the makefile, tell the compiler to do vectorization, and let it be done. Okay? But sometimes the compiler doesn't recognize the code pattern or doesn't think that there is a problem in the code and doesn't vectorize. Then you can either use the corresponding command line options, or you can tell the compiler so-called vectorization hints, like pragma ivdeb, or pragma vector always, to tell the compiler, hey, this is safe code, do it. Okay? But still you leave the decision on how to vectorize up to the compiler. You just tell the compiler that it's safe to do it, but not how to do it. The next step will be pragma SIMD and SIMD function annotations, where you explicitly tell the compiler how to vectorize. Okay? So what to actually do to the source code. Then we have SIMD classes, at least in C++. It's kind of overloaded operators that boil down to something on the machine level. Right? So we have a vector class that can hold 4 single precision values, and then we got an add operator for it. We have vector intrinsics. This is something Chris will talk about in a minute. And obviously we have assembly code. So you can go down from lazy to very, very complex. And of course, this up here is easy to use. It's just a compiler flag. This down here is not so easy to use, but you've got full control over the machine. Okay, so our recommendation is to stop somewhere around here. Okay, so first try automatic vectorization. If that doesn't help, go down one level and try to help the compiler through compiler options or annotations. And if that doesn't work, tell the compiler how to vectorize. Not necessarily go down and re-implement your Fortran code in inline assembly or something. Okay, that's probably not the way to go. Okay, aliasing. Chris already mentioned that after the composer session. So we have a different series of options to tell what the compiler should assume in terms of aliasing. Fortran is a nice programming language because there are no aliases. Well, you can have them, but it's your fault, basically. The language forbids them. If you create them, it's no longer a Fortran program, basically. It's written in Fortran syntax, but it's no longer conforming to the semantics of Fortran. And for C, you got something like alias args, NC alias, no aliasing, no function aliasing, the restrict keyword. So these are all options to tell the compiler what type of aliasing to expect. If you don't say anything, the C compiler basically assumes that a pointer is pointing somewhere in the memory, and if it cannot detect where it points, it assumes that it overlaps with anything else, right? If you tell the compiler, hey, it's only NC aliases that we have, it would assume that it adheres to the aliasing rules of C99. That is, a pointer points to the beginning of an array, and if you do pointer arithmetic, it will be only inside that array. Okay, that kind of stuff. Or you can say there are no aliases and go down the Fortran route and forbid aliasing completely for the C program. This can be dangerous because some C programs actually have aliases in there. Okay, this is an example on how to use the restrict keyword. So this tells the compiler that B is a restricted pointer to int, and restricted in this case means it doesn't overlap with any other pointer. Okay, which is not true for A. So A might still overlap with B. but B will not overlap with A. Okay? And then you can probably do something around the optimizations. You can also add that to the bracket syntax and that kind of stuff. This is, again, the loop not countable example. So here we have an integer, B and D. We have an integer pointer here, and alias analysis will tell that this A pointer might overlap with this B pointer, and when we modify A through this assignment, we might also modify that variable. Okay? To avoid that, we introduce a temporary to store the value. Now the compiler sees that UB is not changed inside the loop, and it knows that the loop now can be counted and vectorized. Okay, and then we have SIMD directives. It's like an English test. So the relation of automatic parallelization to OpenMP is like pure automatic vectorization to user-mandated vectorization. So basically, we use the same idea of OpenMP to specify how to parallelize in the SIMD space, where we provide pragmas to tell the compiler how to vectorize the code. Okay? So for example, here in this case, the compiler can again not vectorize, although the loop seems to have no dependencies. The dependency might come from the fact that A, B, C, D, and E might overlap. And sometimes the compiler does an overlap check, if it can do that. For 5 elements, it's just too complicated, so the compiler would just tell you, hey, I cannot vectorize that part of the code. And you can add a pragma SIMD in this case, to tell the compiler that there is no aliasing and that it can vectorize. This is, basic stuff. But what you can do is you can tell the compiler what the relationship of variables and code statements is. Like, for example, you can tell the compiler that a certain variable is a private variable. Okay, so it may replicate it as many times as needed without assignment, without introducing an intermediate value or anything like that. It's just a temporary, replicate it how many times you want it. Or you can tell that there is a variable that is depending on the loop counter with a certain step width. So whenever the loop counter ticks once, this variable ticks so many times. And now the compiler knows that when it replicates the loop body 4 times, it needs to replicate the variable also 4 times, and it also knows the step width for each of those replicas, and how those replicas need to be updated every time the vectorized loops runs through an iteration. Or you can tell the compiler, hey, this is a reduction. So whenever we have a variable v, and we add them up in terms of a residuum computation or whatever, you can tell the compiler to do a reduction of that variable from the vectorized version down to a scalar version. Yeah.
How much stuff can a loop vectorize? Does it matter how much stuff you have in a loop that you vectorize?
Yes, because the more stuff you add to it, the higher the potential that the code becomes too complex. And there's no fixed limit on that. But usually, when you add if statement cases and whatnot, at some point the compiler will not be able to figure out any longer what the loop does.
So is it better to make 2 loops instead of 1?
That's also not true. Sometimes it is true when the code becomes too complex and you can split the loop and create 2 vectorizable versions of the loop. Then yes, but it's not a general write this kind of that kind of loops, right? Just single liners or anything like that, right? So, it depends on the vectorization report. So the compiler will tell you when it starts not recognizing the loop anymore, and then you can think about it if you can split the loop, or if you can introduce a pragma to automatically split the loop, for example. We also have pragmas to do that. So there's no need to actually create 2 loops out of it. This is an example on how to do a reduction. So because of floating point precision, the compiler may not be able to figure out that this is actually, vectorizable with a horizontal reduction across the vector register to produce the final sum. And you can tell the compiler, use sum as a reduction variable. It's safe to do that. Okay? And you also pay the precision loss, because you told the compiler it's okay to lose some precision by adding up the floating point numbers in different order. Okay? Something that the compiler wouldn't probably detect. Okay. Okay, the other thing is we have section notations. That's kind of the idea of Fortran with array notation, and we do that in C. We do it differently. We do it with C-style semantics. So for example, in Fortran, it is lower bound, upper bound, right? In C, it is lower bound, length, and stride. The reason for that is that C is, first of all, a zero-based language, and all the APIs and all the pointer semantics in C are zero-based and length-based, not upper bound-based. So when you declare an array with 10, you get 11 elements. 10 elements, and not, from 1 to 10, right? So basically, the syntax is the same. The semantics are a little bit different. And so you can describe, for example, all the elements of vector A, all the elements from 2 to 7, or elements starting from 0 to 4. That's 3 elements with a stride of 2. Okay? And you can use that together with all the standard operators in C and C++, like plus, minus, multiplication, division, and so forth, to basically describe array operations on that level, and you can easily avoid the loops around the vector operations. And at the same time, now the compiler is able to figure out that that kind of statement can easily be vectorized. Okay, that's the idea behind that. We also have reductions, horizontal operations across the vector register or the vector, like adding up all the elements in the array, or finding the minimum or the maximum or the minimum position, whatever. And so this also gives the compiler more knowledge about what the code is actually doing, right? If you write a loop, the compiler sees a loop. And it needs to stick whatever direction the loop runs or in which order it processes the elements. And with that, you can tell the compiler process this array, and I don't care about the order. That's the idea behind it. Okay, and then improving vectorization, alignment. So alignment means where a particular variable starts in the memory, basically the address, right? And vector registers work best when the data is aligned to boundaries of size of the vector register, right? So if the vector register is 16 bytes, the data should be aligned on 16-byte boundaries. If you don't do it, we need to load 2 16-bit chunks and assemble them in the vector registers. And this is kind of, overhead inside the CPU that costs some additional cycles. Okay, and the compiler tries to be as smart as possible. So it tries to generate a loop with alignment, and it tries to generate a loop without alignment. Given that it can detect if the data is aligned at runtime, works for 1 pointer, works for 2 pointers, for 3, 4, 5, or 6 pointers, it doesn't work anymore. Too many versions, okay? So you can fix that. The first tip here is align your data, okay, as much as possible. 32-byte boundaries or 64-byte boundaries are best for different architectures. Okay, how you can do that? That's really easy. There is a mmmylog. That's an intrinsic coming with the Intel Composer and GCC. I don't know if Cray implements that as well on Intel. The mmmylog. Okay, so you do it automatically, right? So POSIX usually doesn't have a malloc requirement on alignment. It's just alignment on the base type. That's important. I'm not sure about Okay. So with mmmylog, you can give an int base argument, which gives you the alignment, basically. Or you can use POSIX memaligned to align a pointer to it. And then you can use pragma vector aligned to tell the compiler that a certain pointer has been allocated with those functions and that it should assume that this data is aligned. There are also different versions to do that, like declspec attributes or GCC attributes or compiler assertions where you can tell the compiler it should assume that something is aligned. So there are always different versions depending on which programming language you use. So typically my recommendation is to use the pragmas because they are ignored by non-Intel compilers or by compilers that don't understand the pragma. And you get a similar pragma or directive in Fortran, basically, whereas this is only understood by the Intel compiler and would give you a compilation error when triggered. Okay, this is for Fortran, as I said, directive vector aligned. And you can specify basically the same at the allocation side to tell the compiler or the runtime system basically to align the data when allocated and then access it in a aligned fashion. Yes?
So a question about the array syntax in Fortran. So Fortran 90 was designed specifically for that to enable vectorization, vector compilers in those days. However, what we learned was that the compiler could do a better job if you didn't use array syntax. So are you saying for Intel Fortran it's now better to use array syntax, or you can't generalize it like that?
Fortran expert. No.
And I think it's sort of, I think if you're talking about alignment, it's an orthogonal issue.
No, I'm not talking about alignment.
Okay.
Just in general, whether vector array syntax is in now, should be using array syntax in Fortran programming.
Well, one of the problems is that and that's also why we changed the semantics of array syntax in C, that the way Fortran describes the semantics of array syntax, basically, and this is why the manual loop is better, because manually you can avoid temporary copies of the arrays. And the compiler cannot do that in all instances when you write it down, right? Because of the semantics, how Fortran 90 specified the array syntax, like evaluating the right side in the first place, and then write the final result back on the left side. Okay, and in C, we specified, well, this is an element-wise operation, so you just need to compute the right-hand side element, and then you can store it into the left-hand side element whenever you want, right? And so this in C we can avoid the copy, and if you code it manually, you can prescribe when the update actually occurs on the left-hand side. That's probably why you still need to write it yourself in a do loop.
Yeah, he's exactly right. I mean, when you had array syntax, you had a series of statements, and you were relying on the compiler to first fuse them, and then sometimes even after fusion to eliminate the left-hand side when possible. Where if you had just written it as a do loop, you might not have, those left-hand sides might have been scalar temporaries. Then the challenge for the compiler would be to promote them to a vector, but they got pretty good at that part, you know, and would never have stored it back to memory. So that's kind of the challenge there. Now, I will, since you had already mentioned it, this is one of the reasons behind do concurrent. This might be a little bit in the future because do concurrent is just becoming available, but Fortran 90 also had for all, right? I hate for all because it may give you the impression that you were writing efficient code, but it wasn't. It basically says take everything into for all and turn it into array syntax, and then the compiler still had this problem. The do concurrent says this is a do loop. I can have scalars in the do loop, but it no longer has dependencies, so it gives the compiler more information as opposed to less information. So these are little subtleties in there. Array syntax is great for one-line things, copying and stuff like that. But if you have multiple statements that naturally group together, I would probably recommend do loops.
By the way, same argument applies to the OpenMP workshare construct in Fortran. It's hilariously broken. Okay. Didn't say that loud though. Is this recorded? Okay. So, you know, this is kind of just showing that alignment issues can occur anywhere. So the basic idea here is that depending on whether it's row aligned or column aligned, one of the dimensions will be aligned and the others will not. That's the essential part of it. So it really depends on what number of columns you have. If it's a multiple of 16 or 32 bytes, it's fine. If not, the second column will not be aligned, or the second dimension. Okay. Okay, my little thing here doesn't work anymore. Here's another example on the effect what alignment may produce as an outcome. So the first code path is aligned, the other is not. Okay, and so what the compiler does is, if it is aligned, it can use a special move instruction to move the data from the main memory back into from the register back into main memory. And it is able to detect that it is even non-temporal store, so the data is no longer needed, right? If you have unaligned data, the compiler needs to do an update operation and then extract the data back into vectorized form. So this is an additional instruction that costs latency or execution cycles. And this will be more complex for the machine to execute. Okay, so whenever possible, please align the data. It's probably also a good idea, if you go back to that example, if column width is not a multiple of 16 or 32 or 64, whatever, it might be worth the effort to introduce padding into your data structures to make the second or third dimension aligned again. Okay, at the expense of memory, you can get back performance. Okay. Okay, that's about. Yep.
If the code is not aligned and you force alignment, will it
It will crash. So this instruction will raise a execution exception, segmentation fault, bus error, illegal instruction, whatever, depending on the operating system, when triggered on the wrong data alignment. Okay. And one of the big things we did for Nehalem and Westby was to optimize the unaligned loads. Right? So in former times, they were really, really painful in terms of execution cycles that they needed until they completed in the pipeline. Now they are only twice as much as the aligned load, which is a big step for us. And with out-of-order execution and pipelining and that kind of stuff, you can go down to probably 10% of efficiency loss for an unaligned load, if you can overlap it with other instructions. But still 10%, it's 10% of your machine. Okay, so aligned loads are still a good idea. Okay. Chris.